right? So that way you'll have repetitive thing. All right, so we should be recording now. I did one of these the other day, and I forgot to hit record. All right. Anyway, so we're ready. So now this week we are discussing the topic of Hadoop, right? This can also be discussed called cluster computing, map reduce, which is actually like the theoretical idea that we're going to explore, or parallel computing. All of these are kind of the same area. This is a big topic. There are really great books about this. There's essentially two approaches um, to parallel computing. One is going to be using GPUs, and one is going to be, clustered GPUs, and one is going to be, well, yeah, one clustered GPUs and one clustered CPUs, right? So in our example in this class right now, we're going to look at the idea of clustered CPU. And for clustered CPU, somebody developed this framework called Hadoop, right? So the idea, the theoretical idea first was something called map reduce. That's kind of how you should think about parallel coding, and essentially then they built this tool in Java called Hadoop. Okay. So Hadoop is just the implementation of the ideas of uh, map reduce essentially. And it's used for CPUs. So the story goes that this kind of started out at Amazon.com, right? So Amazon.com back in the day, would have a lot of servers, right? They have a lot of servers. They're selling, hosting things, their databases and their web pages to sell products. All right. And then obviously sales are seasonal, right? So February, sales are pretty low, and they maybe had enough servers for peaks in, let's say, September, October, right? But then came something like the holidays, right? Black Friday, November, December, all of that. And then what would happen is they would run out. The servers just didn't have capacity, right? So people, too many people trying to access the servers. Do you see that? They were probably running Linux, running Apache servers, MySQL, and so on. But they were running out of capacity, didn't have capacity for those peaks, right? So that's Amazon. So what do they have to do? The only solution is buy more servers, right? So they buy more servers, and now come November, December, they have enough for sales. But what happens in February? You have all these servers not doing anything, right? And so then they start thinking, what do we do with these servers in February? And that's where cloud computing essentially was invented. Right. So it's like, okay, let's just rent out these servers in February. And that's that's essentially how cloud computing came to be. And the same goes for Hadoop and these services. And they have a lot of data that they want to process. They've collected massive amounts of data. They have all these web servers sitting, right, just doing nothing in February, not even for the cloud services. So they're like, if we could process this really large job on all these computers all at once in parallel, right? Because we have them, right? And so that's essentially why this solution was invented. You guys see that? Because there are other solutions, like there are GPUs, you can cluster GPUs, but that's, who would have GPUs? Maybe someone that was into gaming or machine learning, but something like Amazon, they weren't really gaming, as far as I know, right? And so, but they had all these CPUs, so they just said, "What do we do?" And so they invented this idea of cluster, map reduce, and they invented these protocols essentially for Hadoop and these ideas, so that now they take all those CPU-based web servers, put them in a cluster, and use them for some parallel computing. Does that make sense? So, yeah, go ahead. Okay. Right. Sure. Okay. Well, I mean, spinning up, no, well, actually, spinning up servers is just spinning up Linux machines. And then Hadoop is just a software that you install. So you have to install it on every machine, and then you have to configure it so that the machines talk to each other. It's essentially a protocol of managing tasks in parallel. Yeah, so if you go to AWS, it's the same as going to your three, say you have three VMs on VirtualBox. Turn them on. Right now you have C1, C2, C3. Running Linux, no problem. Go to AWS, Linux 1, Linux 2, Linux 3. Bring them up, right? But then you have to configure the software, right? So you go and install Hadoop on each one, and then you have to, that's what you will do actually for project A is configure each one. One has to be like the manager, right? The master machine, and the other nodes work for the master, if that makes sense. So you need to set up SSH, you need to set up accounts, you're going to create something called a distributed file system, HDFS. The nice thing about that is that Hadoop is going to manage that for you. You just have to set it up on each machine and say, okay, this is the master, that's the IP, these are the others, the nodes of the workers, and then you establish some kind of SSH key, etc. And the machines know, like, the master will get a job and it'll distribute it out, communicate via SSH, and reduce the data and provide an answer. So yeah, so Hadoop is a software that runs on Linux machines. Okay? And you will see that. You will see that, you know, in project. Right? That's the challenge, right? So it's not trivial. I think pay attention to it, start early. Because it'll be smart. All right. So what I'm going to do today is I'm going to go over all the theory on this. I'm going to go over the problem. I'm going to motivate the problem and what's going on in the background. And we can actually solve this problem on the terminal of Linux. The problem is I'm just going to give you some two, three books from Gutenberg, right? So you can process that very easily. Well, what if you had a million books and you had to process that same data? It would take a very, very long time. So that's kind of the candidate for your cluster. You see that? Now, another thing is when you do parallel computing, you can't solve every problem in the world with parallel computing, right? You can only solve specific types of problems. So, for instance, when they talk about quantum computers and everything, they say, oh, they're going to revolutionize the world. Well, as it turns out, quantum computers are good at solving very specific problems, not every problem, at least currently. That may change over time. The same goes for GPUs. GPUs perform matrix multiplications. That's essential for computer graphics, for machine learning, right? But it's a very specific operation. Here, we're going to learn that, not everything requires parallel to be parallel, but I'm going to motivate a problem, which is word counting. Essentially, we're going to count the number of words in all these books. So you can count all, how many times you see the in one book in parallel to how many times you see the in another book. You guys see that? So I can give this computer a very fit and tell it to count how many times it sees the. And I can give Dracula to this one, how many times I see the word. And then once I get those two totals, I just combine. So that's essentially what MapReduce is. Okay? So that type of problem you can implement in this environment. And that's the one that I'm going to motivate in this class today. Make sense? So that's what we're going to do. But not everything. If the problem is sequential, you're probably better off just doing a CPU, one CPU. Yeah. Of what? Of uh, something where you would use parallel computing. That's a good one. What's that? No, video games are actually parallel because you take one mesh and you multiply it and you move it in another mesh and multiply it and move it and then combine it. So, yeah, that's a good one. Sequential is previous something like counting, right? Like I said, counting. But if I maybe something that's this is just one example that comes to mind, something that's dependent on time, like a time series thing. It's very dependent on the previous one, so that's very sequential. So, yeah, I'm getting some signal. I need what I've gotten before to be able to predict the next thing. So I can't parallelize that so well. Yeah. Yeah, I don't have a great example, but yeah, that's a good question. But yeah, not every problem can be done like that. All right, so that's the idea. So we can take a look at the links first just to see. I'll be using my whiteboard, and then we'll switch to the VM. Okay, so here we are. These should be my notes. When you have this, it looks blank, you have to download it. Yeah, it's a power. You have to download. All right, so yeah, so these are gonna be my notes. Um, and you can run the slideshow, right? And this one also, it's gonna be the coding part of it. All right. Um, this is gonna be the homework assignment, so I guess I can cover this, but I'll get to it. For this homework assignment, you do not need to use Hadoop. You're just trying to understand the basic idea. So problem one, use some books from Gutenberg.org. So you can go to Gutenberg and download these plain text files in UTF-8, and then you're going to give them to the scripts that we're going to write, and we're going to perform the frequency count exercise. Yeah, and we're going to go back to the command line, the command pipeline approach to implement this idea of using a mapper and a reducer function. So essentially, this map reduce framework was created so that you could solve problems that are parallel. And so you have to think about it. So you'll see that. Yeah. Go ahead. Yes, this homework you have to submit a week from Wednesday. Yes. This is the homework. This is a lab, and this lab just shows the main idea, and then you guys will do a project where you do the exact same thing, but in Hadoop. All right, problem two. Modify the mapper and reducer functions that were provided in class so that you can perform the frequency count, but this should be done per book. So now you would have to do, instead of all the books, would have to do on a per book basis. It's similar, but a slight difference. Do you guys see that? I will only demo problem one. So you have to figure out problem two. Okay? Any questions on the, right? Yeah. So again, you won't have to use Hadoop for this one. Just we're gonna do everything on the command prompt in Python. All right. So that's essentially that. So now I'm gonna switch the whiteboard. Okay. And then whiteboard. So I'm going to start with some ideas. These apply to any kind of parallel computing. These are just like basic ideas of what you want to do when you're doing parallel computing. They have to do with the problems of moving data around. You have to make the assumption that you're looking at massive amounts of data. In fact, parallel computing is not useful if it's very tiny. If the data that you're using, might as well just use CPU. But if you have massive amounts, I mean, 1 million books, right? Something like that. Then that's where you start to get a benefit. All right, so the pencil works. Change the color. All right, so we're going to start. So the very first idea is we're talking about Hadoop. Okay. Um, and Hadoop is just an implementation of this idea for cluster computing called map reduce. So essentially, it's a two-step process where you first take your data and you map it to a specific format, and then you perform an operation, and then once that's done, you reduce. Okay, so we will code these. So map reduce. All right, so what do we have to understand? So we have storage capacity, right? So we have like a hard drive. So that's a computer, right? Imagine this, the CPU, the computer that we're using will have a CPU, we'll have RAM memory, and then we'll have storage, like the hard drive storage, right? And we're going to call these computers nodes essentially. So the problem is here, we want to process a lot of data, but what if we have so much data that the data just doesn't fit in memory? That's essentially the type of problem that we're dealing with. So in that case, we will have to read the data in batches, right, and organize it. So we'll have to take all the data and distribute it out in batches, which is just like uh, sections of the data, and we have to think about how we're going to place it on our individual computers. So a cluster architecture is essentially, you can imagine you have 16 to 64 computers all connected together via a switch. So it's all normal connections via the network, right? So there's no special thing. Like you're not creating, the whole point is that you're not changing any hardware. There is no new hardware device that comes in here. You remember the Amazon example. You still have a regular network architecture, and you implement software that will actually solve the problem for you. So you have, let's say a couple of computers here, and these computers are connected via a switch. Right? So you have to make sure, obviously, that there's network connectivity. And this is going to be similar to what you guys will do in your lab, right? So you'll have some connectivity, and then you can have essentially maybe another switch. Switch, right? And you have a couple of computers here. And then these can connect in some way as well. All right. But essentially, you build this cluster with normal networking technology, and the software is what does all the heavy lifting. So we have to think that, companies like Google, Amazon, etc., Facebook probably have millions of computers like this. Okay, so they literally in GPUs the other day, I heard that they bought they were trying to build just one cluster of 650,000 GPU boxes, right? So, so they're pretty big. It's a very hard skill. Like anybody that just building that network, that actual hard, they get paid really well. It's hard. All right. So essentially, so we're talking about that. So now what we have to think about is that when you're building a cluster like this, there's going to be problems, right? There's going to be difficult things that need to be solved. And these are the things that drive a lot of the ideas. So there are several issues. Okay. So I'm going to create a new page. I'm just going to say issues. with a, with the cluster, right? So issues. All right, so we have some issues that need to be solved. One of the issues, of course, when you have 1,000 computers running, what's going to happen? Some of those computers are going to fail, right? So computers fail. So we're going to say nodes fail. Because of that, you're going to have redundancy. Who does the redundancy for you? Hadoop, right? So that becomes one of the reasons why we need to have something like Hadoop, because Hadoop is going to start handling the redundancy for you, which essentially means it's going to take a batch of data and put it on this computer, but it's going to create a backup and put it on that computer, right? And it has to have a nice protocol that can coordinate all of that so that if this machine fails, that one still works and it can still finish the job. Does that make sense, guys? So that's essentially the idea. So you can assume, for instance, a statistic where if you have 1,000 servers in a cluster, you can expect, probabilistically speaking, that you'll have one failure per day, okay, in a cluster of 1,000. So that gives you a nice little statistic there. So if nodes fail, the approach needs to deal with this issue, of course. So that's one of the issues. Another issue, number two, is the network bottleneck. Okay, so the network bottleneck. So let's think about this idea, right? So let's say that you have a computer, a laptop such as this, or a PC or whatever, and you have two CPUs on it. So you can do parallel computing with those two CPUs, right? Data is being sent to one CPU and another. How do these two CPUs communicate? And how do they access the RAM and the hard drive? What do they use? They use the motherboard, right? They don't have network cables at that level. They have a motherboard. And on the motherboard, what do you have? What is the name of the thing that connects all of those things, like the hard drive and CPUs and the RAM? What's the name? It's called the bus, right? On the motherboard. That bus is really fast. It's really, really, really fast, right? So that's designed to be fast. On the other hand, when you have a whole bunch of computers like this, all these computers are connected to a switch via network cables, etc. They're not as fast as a bus in the motherboard. You see that? Now, companies specialize in creating specialized types of networking cables for connections that are very fast. For sure, NVIDIA has some like that, but essentially that is the difference. The network is a bottleneck. So let's think of the example, let's say that you have one computer that specializes in doing a calculation. Do you want to send, let's say you take all your data, right? Let's look at all these computers here. We have about 20 computers and we have 1,000,000 books. 20 computers, 1,000,000 books. So we give each computer, what is it, like about 50,000 books in each computer, right? So then we have to, okay, great. We've distributed out the data in, 50,000 books per computer out of the 1,000,000. And then what do we do? Let's say we need to count, we need to multiply, so should we have a designated computer? Let's say that one over there in the corner that does the addition, and then that one does the multiplication. And then do we just take the 50,000 books, send it to that one, then 50,000, send it to that one? Do you see where I'm going? To do something like that, that means 50,000 books would have to get in the network and go over there. Then another 50,000. You see that? That's going to be on the bottom. So that's a problem. So a problem that needs to be addressed, and it's critical. So if the network bandwidth is gigabits per second, then moving 10 terabytes takes approximately 1 day. Think about that, right? So you have the speed of your network, you have the amount of data that you're sending. Moving 10, if you have 10 terabytes on this computer and you want to move it, it would take literally a day to move the whole thing, right? So that's an issue that needs to be solved in some way, but that gives us the issue of network bottleneck, right? So that's problem number two. So you need an architecture that does not move the data too much. So that's going to be the thing that we need to think about, right? So, and that changes how we do things. And then number three issue is going to be that distributed programming is really hard, right? So parallel computing is hard. Okay, if you're programming on GPUs, right, and you want to do parallel computing, you use something called the CUDA library. Pretty difficult. That's why if you guys take 365, etc., we look at things like PyTorch. PyTorch makes it a lot easier because it's abstracting a lot of the parallel computing. Here in Hadoop, we're actually going to have to program in parallel. It's kind of a very simple problem. And how do we solve that? We use something called map reduce. Map reduce is like the philosophy of how to code for parallel. You see that? You have to think about that. So we need a simple model that hides most of the complexity. Okay, so we need something like that. So we're going to say here programming, distributed programming, is hard. And so essentially these are the three main problems. There are others, and then we're going to look at the solutions that we have for this. Okay. Um, so people have created very smart people invented this idea, this philosophy called map reduce, which addresses all three. And then other people then decided, okay, let's implement this. And they implemented the Hadoop framework in Java. All right, so now let's take a look at how MapReduce addresses these three challenges of cluster computing. Okay, so MapReduce, MapReduce, right, addresses these problems. Right, so the first problem was nodes fail, right? So what's the solution to that? Um, redundancy, right? So that's gonna be actually I'm gonna write this in the second. All right, so then how does MapReduce address these? When nodes fail, you're gonna want to store data redundancy. Redundancy. So that means on multiple nodes for persistence and availability. So you're going to take a chunk, a batch of data, and put it on one machine and create a copy of it in another one. And Hadoop does that automatically. So you don't have to do any of that. The framework is supposed to handle that efficiently. The next problem is network bottleneck, right? So the network bottleneck, so MapReduce addresses that by moving computation close to data to minimize data management. So instead of moving all the data from one computer, you move the program to the computer. Do you see that? So it's going to be like you have a script that does the logic of taking the data, processing it, and producing a result, right? That's the software, the program. So what you do is write the program, and instead of sending the data to the program, you send the program to the data. So you will say, this has a batch of 50,000 books, that has a batch of 50,000, 50,000. And what you do is you send a count function to all of them so that you do not move the data. You do the processing there. And once you have the results, that's going to be much smaller usually. And that can be moved across the network. Does that make sense? So that's essentially happening. So move computation close to data. Let's say computation close to data. Compute to data. Give me a second. Yeah. What's that? So you'll have 50 books. You have a million books total, right? Imagine a million books, a library. So you give this computer 50,000 books and that computer 50,000 books. Now, what you're doing is you're going to count the number of times that you see each word, right? So you essentially write that program and you send it to every machine. So now this machine will get the program and it'll count all the words for just the books that it has. And then this computer will do the same for just the books that it has, and so on. And then once you get the results of that, that's the reduce part. So it's like you collate the results from here and these. So let's say you have the equal 100,000 and here the equals 60,000. So then the becomes 160,000. You see that? So that's how you do it efficiently because you do not want to move the data across the network in this framework. Well, I mean, just write a program that just looks at those books and it provides a result. As I said, it's only meant to solve certain types of problems. So this is one problem that illustrates that. All right, and then the last part is distributed programming is hard. So you need a simple programming model to hide the complexity of this idea of a parallel, and that's going to be what we're going to use mapper and reducer functions. So we're going to actually your code is going to be written instead of one script in two scripts, right? And so essentially that's MapReduce. You have a map function that does the data into a format, and then the reduce function that does further processing. So I'll demonstrate this, but it's going to be the mapper and the reducer. Okay, so that's it. I mean, that's the essential idea. Okay. So the other thing that we have, we have the issues, nodes fail, network bottleneck, and distributed programming. So we want to have redundancy, copies of all the batches, compute close to data. So once we put data in there, we don't move it. We don't move it to another place. The 50,000 books live there from now on, right? and essentially the program is there. Now, one nice thing about that is you don't have to essentially like say, okay, I'm going to transfer these books here and those books there. Instead, you build a cluster in Hadoop, and then Hadoop, because all these machines, these 20 machines in this network will have Hadoop running on them, and you will have one that's the manager. The manager will essentially then say, okay, I have all these computers, 20 that belong to my cluster. Every one of them has their own individual hard drive. Now I'm going to go ahead and create what is called a distributed file system. See, it's called the HDFS, so the Hadoop Distributed File System. And so this concept is really nice because in the manager computer, you will have, you know how we go and we see the hard drive, right? And we see everything, all the drives in the file system. Now you're going to have a new one, which is going to be a virtual file system. This file system does not exist physically on the machine. It is just a distributed thing that you can only reach through Hadoop, but essentially it's connected to all the hard drives of all the computers. Do you see that? And Hadoop creates that for you once everything is configured correctly. So essentially, when you guys run your job, and this is related to the project, once you create the HDFS, you will just put your files in like a specific place, and Hadoop takes care of distributing that to all the machines. Does that make sense, guys? So essentially, it's like you have the manager and you say, this is the mapper function, this is the reducer function, this is the data. And Hadoop distributes it, sends all the data to all the machines, sends the code to all the machines, and that's it. All right. So yeah, so that's essentially how it works. So the distributed file system provides a global file namespace. It provides all the redundancy, all the availability, and distributes the data in batches. So some characteristics of the Hadoop HDFS. So remember, these things, if you think about it, you're used to working with laptops, right? And things like that. So these are not problems of a laptop. They seem almost like silly to worry about these. But if you have hundreds, thousands of computers, massive amounts of data, then all of this is significant, right? So the Hadoop file system reads are common, right? So it reads a lot, but not that many updates and not that much file distribution, right? So it's meant to be efficient that way. The distributed file system will take the data and it's going to break it up into chunks. That's the term that it uses. And it's going to spread those chunks across all the machines in your network. Okay? So a lot of these things seem complicated, but Hadoop does it for you. So that's why it's nice to be able to set it up. Each chunk will be replicated on different machines as well. Right? So we'll take a look at this idea. So essentially, this is pretty simple, but say we have a file, right? So we're just going to break it up into parts, C0, C1, C2. So that's your file, all the books, right? Imagine you have 1,000,000 books and you're breaking it up to 20 bins, 20 batches. And so this is C20. Right? And, it'll have different algorithms that it uses for this. But essentially, then you have your individual servers. As you have like server 1, and then you have server 2, dot, 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 until server n, however many servers you have. And Hadoop will just take care of doing all of this and distributing out the batches. What's important is it'll create the redundancy. So for instance, C0 might be here in this server, but it's also over here in this one. And it has been replicated. And so the manager will handle this, right? So it'll create a job, It'll expect this job to complete. If it doesn't, and too much time uh, goes by, maybe it'll ask if it's working, and if not, it'll go to the other machine that contains that data and ask it to complete the job. You guys see that? And then eventually, all the job should be finished. But you have to have this idea of redundancy. And just remember that these servers perform the computation here. So both this is a piece of a computer with its own CPU, right? CPU and storage. So the hard drive, the disk. The program that's running on this CPU is only processing the data, this piece of the file in this disk, right? And nothing else. All right. Yeah, so that's some of the theory of it. And then we're going to move into the coding part of it very soon. Motivates the idea, right? And it should be pretty straightforward. So this is a simple concept. We've talked about Hadoop. We've talked about the project. So some common issues with Hadoop when you guys are doing the installation. One of them is that it'll use symbolic links. It has a symbolic link to Java. One of the hard parts is you probably have to install Java, like the Java library. And those Java libraries are like GRE 2.6, 3.7, whatever it is. So you'll need to have a symbolic link from the word Java to whichever version you install. Okay. So that's one of the things that's important issue. You will have to set up accounts and you'll have to use SSH, which means you have to use a key, you'll have to have keys already exchanged between the machines. All right, so the distributed list, now we're going to start looking at, so these are the ideas, right? So these are the issues that you have in parallel computing, some of the solutions provided by Hadoop, the software. And then you have to implement this distributed program. So let's take a look at that. So let's say coding distributed coding. So essentially the name MapReduce comes from this coding. So we need for distributed programming, we need a simple model that hides the complexity. So here, this is provided by MapReduce, which gives us a basic pipeline of steps. So usually we'll start with the data. That's going to go into the mapping function. So that's going to be the first. The mapping function, it's simple logic. It'll almost feel wasteful. So when you look at the mapping function, it'll almost seem like a waste, but it should make sense. You have to think as the data almost as being wrapped in a packet, right? Because you have to track that data across all the processing that it's going to go through. And so that's essentially what the mapping is. It can be very simple as our example is, or more complex, but essentially like wrapping it through a packet so that eventually that little serial number or whatever it is can be looked up somewhere else or tracked. The mapping usually results in some data that needs to be sorted or processed in some way. The sorting is essential, as I will show you, because it'll provide efficiencies, especially for the problem of counting, for instance. I'll motivate why that's necessary. And then once you do something like sorting, then you do the reduce part. And the code for reducing can be a little bit more, is usually more complex. Okay, because the data is, this is where it's not very, like you're used to with a for loop or something, and in sequential programming, it's going to be a little bit different. So this code we'll look at. And then finally, this provides the results. So this is going to be the pipeline that we're going to implement, and we're going to do that in Linux, essentially. So those are provides the results. All right, so let's take a, so the best way to understand this is going to be to have an example, right? So we're going to look at an example. Um, so we're going to start, the data is going to start with some file or several files. So for instance, let's say doc.txt. For a lot of the examples, we'll be using Gutenberg, right? And so we can download some books and have, a good amount of data. All right, so let's start with this example then. Okay, so we have step one, we have some document. And the problem, of course, is we're going to count words in parallel in this cluster. Count. This is also, you can do probabilities, for instance. You want to find out the frequency of the occurrence of some word, right? So the car. So how often does car occur after the versus the is, not so common. Do you see what I'm saying? So you calculate these probabilities, and that can help you to develop some kind of a model. But anyway, so in this, the easiest to understand is to count words. So I'm going to start with some file, doc. I'll even make up a very simple document initially, txt. The next step is going to be that we're going to take that data and we're going to map it. So we perform the first step, which is to map it. Right? So that essentially, we extract like records, key value pairs. You can think of it that way. So we can now create, the is the value, right? But we can create a key value pair where one of the items is an ID and the rest is the information that we're carrying. So that's a good way of thinking about it, as creating key value pairs of any format. You define the logic. This is just or even more complex than this. After you establish these, um, you essentially can group by key, right? So for instance, all the, whatever it is. So grouping and sorting are next steps. So group by key. Group by key. You can also sort by key, etc. But you usually have to do a step like this. And then step 4 is going to be the reduce function, which is a separate function. And this function is the one that just aggregates, summarizes, takes the totals, etc. Right? So this is going to be um, the last function, which in our example is going to be somewhat difficult. Aggregate summarize, etc. So those are the steps. So now let's try to visualize a simple example, okay? And then we're going to switch over to the virtual machine and start writing our code for this, okay? It should be pretty easy. So I'm going to create a new page. So we have key value pairs. We have key value. Think about better. All right, so it should be charging then. All right. So we have key value pairs, and we're going to have something like key one, key two, or K1. So let's say K1 V, and the V is variable, it can be anything. Then you have another key, key two, with some value, and then you have key one again. You see that? So this is what the mapping does. So for instance, key one could be the word the. So it finds the and something, then some other word car, then the again. So it's going to map them into this specific format, and then it's going to essentially group them or sort them. So we can say sort or group, and now essentially it just does this. Now we have key1 B, and sorry, K1 V, and then K2. You see that? So that's all that's happening. A lot of it is creating the entity, the key value pair, grouping them, organizing them, and then start processing them efficiently. The reason for this is that, let's say you're doing a count. If you want to count K1 and K1, so you would have to, if you don't sort it and group it, you would have to iterate through the entire list. You see, imagine if this list has 1,000,000 words, right? And you would have to go all the way down until I find K1, then again all the way down until I find K1, and so on. And so that would be very inefficient and very slow. So this is one of the steps where in parallel you have to think different. By sorting it, now you have all the K1s together, all the K3s together. So now if you find one K1, you just add those until it changes to K3. And then that's it. You see that that's a very efficient way of doing something in parallel. Do you guys see the point there? So if I had to find, let's say that there's between here, there's like 100,000 entries, and then there's another K1. But you don't know that, right? So to add those, you would have to literally find this one, then iterate again through the whole list, find this one, then iterate again through the whole list, find it, and just be slower. Whereas if you organize them, all the K1s together, then once you find one, you add all of them, and that's it. And then you move on to the next. So computationally, it's much faster. And that's the whole point, actually. This is really important. Seems trivial, but this is what makes this job run in a day versus a week or something. Yeah, go ahead. This is where actually we can do this in Python. Java is just Hadoop. We are actually writing our scripts in Python. The map and in any language, actually. So Hadoop is just a framework that provides the communication between the nodes, the data distribution, redundancy. Then you have to give it the code, and then the code has to be a mapper and a reducer function. You see that? And that's it. So Hadoop does a lot of the heavy lifting, but you still have to write this script. So this is just one example of counting words. Obviously, there could be 30,000 different problems you can solve like this, and the logic is going to change. But you have to think about doing things efficiently and faster. Like if you implemented your code and don't do the sorting, it would work. But let's say you're predicting the stock market, it's probably too slow, right? And so you're leaving $1 million on the table. Whereas if you just go in and implement this slightly better version, you get your results the next day, and boom, you short the market. You see what I'm saying? So it's a timing thing. Okay. All right. Anyway, hopefully that illustrates one of the key ideas here, right? With the problem of parallel computing. So mapping is essentially this, okay, guys? Mapping is taking whatever data you have, creating these key value pairs, this format, organizing it, grouping it, sorting it. Once this is done, this is like the mapping. That's the mapping. And then the reducing is just going to be the reducing part is going to be the aggregation summarization. Right? So reducing, the reducer, let's say, reducer. In this context would be what? That now, instead of having K1, K1, we only have one K1. Because now all the K1s have been reduced, right? And so this is going to be, let's call it V reduced R, right? And so that's what reducing is. If we look at K2, there's only one there, but so we are essentially, some other VR. And that's it. Close. Questions? So yeah, go ahead. Well, I mean, what's important here is the K1 and K2. So I took these two and I reduced them into one K1, and I'm adding them. So if this is 3 and this is 2, then this is now 5 or something. That's what reducing is. It's like, but this shows the entire idea of map reduce. Take your data, create key value pairs to provide some identity, then sort, group, etc., and then reduce. And that's just the simplest implementation. Remember, these algorithms are going to change depending on the task or problem. So let's do now to wrap up an example, right? With actual words. So this is, again, we're doing word count here. It's the, the simplest thing that we can think of, but we're going to do it in parallel. We have this. So I'm going to create, so imagine this is a book. So the book, I'm just going to use a sentence here. So I'm going to say the crew crew of the spaceship I'm not writing a grammatical sentence. I'm writing a sentence that has words that I need for the example. Okay. So this is a book. This is the book. Okay. I'm going to call this data or something. So this would be the book that contains this data. Now, I'm going to show you what the process would be. So there's going to be, this is the command line, right? So you would cat, for instance, your book data. So we cat data. And we're going to do what? You know how to use the command pipeline. So we pipe it into our Python function, which is going to be mapper dot py. You guys see that? Then the mapper function is going to produce something, and we pipe that into the next step, which is going to be some kind of a sort. And this shows us that we can, you guys have done df and other functions in the command line, but there's other functions for like sorting, etc. And those are, by the way, very fast in Linux. Okay, very fast. So we want to take advantage of that. Once they guys sort it, we pipe it into reducer. And this is going to be another Python script, reducer.py, that has the logic. So we're going to have to write this code, the mapper.py code, and the reducer.py code, if that makes sense. Yeah, go ahead. The sort is a built-in function in Linux. So we're going to take advantage of a script in Linux to do some of these. Okay? Everyone with me? So yeah, so that's the idea. And what you guys will do, so we're going to do this on the command line just so I illustrate what's happening behind the scenes. And then when you guys implement your project, this statement here, obviously you wouldn't run. Instead, you're going to use Hadoop itself. But Hadoop is essentially doing this but in parallel. Right? So you're going to give it all the books that you want, and you're going to give it mapper and reducer, and it's going to do the whole thing for you. And it would do, it would take 10 million books or a terabyte of books or whatever very fast or faster. All right, so now that we've done this, so now let's think about the map function, right? So essentially, I'm giving you this sentence, right? So we're going to take the crew of the spaceship, the crew, and essentially the first thing that happens is it goes into mapper. So what does mapper do? So mapper will create value pairs. The simplest that we can think of, and this is logic that we are going to write um, in our script. So this is key value, right? So these are called tuples, key value pairs. So what does it do? It's going to do, um, so the first words, right? So it's going to take the, comma, one. So essentially, it made the word for this logic, we can make the word into the key. And the value is just one. Because we're counting, we're just saying there's one dot counting. And if you find another dot, it's going to be dot comma one. And essentially, eventually, those two are going to get added into the final value. So that's what we're doing. So the next tuple would be the next word. So we've done this word, then do this word crew, comma one, right? Then we do the next word, which is of this one, right? I'll continue over here. So I'm going to continue over here. So then what's the next word? It's going to be the, again, do you see that? So it's another the here, comma one, then space, one, right? And we have ship, the next word, ship, one. Then it's gonna be the, and finally crew, comma one. You see that? Seems tedious, right? But if you're writing normal code for one CPU, you wouldn't do this. It would be completely unnecessary. But for parallel computing, it has been found that this is the most efficient approach. So you do the macro function, essentially it created key value pairs for the count problem. Each word became a key, and each value just became one to indicate that there's one instance of that. Yeah, see that? Now, what we do, and I'm just gonna, well, I guess I should continue here. The next step would be to sort these, right? So if you notice this data here, what I have here is the output of mapper.ui. So now you type it into what? Sort. You guys see that? So what we do is we sort it so that we can count these efficiently. We don't want to count the by going, okay, I found one dot. Now I'm going to search again. Okay, I found another dot. Now I'm going to count again. I found another dot. That's too slow, right? And so you need to be efficient. So if you sort it, you guys will see that it's easier to count. But now we're going to sort this so all the dots are going to be together. So that's what I'm just going to move to another page for this. So here, all right. So the one, and then the other so you don't have to implement this logic because it's just a basic sort. That's the idea. The output of one goes into, you type it into the next step, and in the next step, you just take that data and you comma one. So you see that? That's it. And then you do crew, right? So there's two crews in there. Crew one. So that's this crew here, this crew here, and then you have crew again. Remember that what's coming out of one step and becomes input to the next step is data, right? It's like a text file. Imagine that in this specific format, organized in this work. So you need, so for reducer work, this needs to be like this. If you feed this data to reducer, it's not going to work. It's going to have a lot of errors. So reducer is written assuming that the data is sorted already. Okay, very early. So then you have, I did two proofs, and there's one of, and finally there's space and ship. There's space. One, and then there's ship. Come on. That's it. So that's the input. This is the output from sort that becomes the input to reducer. Okay. And then what does reducer do now? Assuming that the data is in this format, is just going to take it's going to look at it's going to look at the next one. Oh, it's the next one at the. Okay. So it keeps adding these. Once it sees that the is changed and has become crew, then it's done with that one and it starts with the next one. And it just does that efficient. So that in the end, let's see if I can. Why I can't create. Word. I guess gonna have to. I don't know why I'm not getting it. Maybe it's limiting me to 7. Let me just stop this and just wrap it up by doing the reduce function to show you the final result. So I'll close here, maybe. Yeah. And then whiteboard again. Board classic. Okay. I like whiteboard classic actually. All right, so let's try whiteboard classic. Yeah, so we were at the mapping. Oh, and look at this. It's much more responsive to my pencil. All right, so we did the mapping, right? So remember the mapping was done, and the final part is the reduce. So we have and this is such a difference. Look, like night and day. Good, discovered something. All right, so and then finally, then we have crew, comma, two, of, comma, one, space, space, comma, one, and ship, comma, one. That's it. That's the example, and that's map read. Okay, so in this example, as I said, the problem that you can do for the project, the problem that we'll do for lab this Wednesday, it's essentially this accounting exercise. It's the simplest that you can do so that we can understand map and reuse. Remember that there are 2 problems in the homework, and I'm only demoing one. You guys have to tweak map and reduce to solve 2. Make sense? All right, so that's the lecture for today. So hopefully that made sense as far as the theory. On Wednesday, we're just going to pick up with Python, and we're going to implement everything on the VM, with one machine, and run through the problem, and then you have problem 2 to kind of try to solve in class. And that'll be the topic of Hadoop. Next week is the exam, as I said, exam 2, and then we'll probably move on to another topic. All right. So we'll stop here for today and have a great rest.